Before we talk about what a limit is and why we need this, we have to know the most common problems in calculus. The first one is when you are given a function and a point on its graph. Find an equation of the line tangent to the graph at point P. And the second classical problem is to find the area between the graph of f of x for an interval a, b on the x-axis. Very often, we will need to find the slope of a line, which is also called the tangent line. It is very easy to find the slope of a straight line function by taking 2 points on the line y2 minus y1 over x2 minus x1, and the slope will be the same for every point of the straight line in graph 1. But when it comes to a curved line, as you can see in graph 2, if you take 2 points on a curve, A and B, and try to calculate the slope, you will not achieve a correct result. But say, if A and B become really close to each other, as you can see in graph 3, and if you use these 2 points to calculate the slope, you will get a better approximation of the slope. And this also means that we want delta x to be very close to 0. So, if you put that into mathematical representation, it will be the limit of f of x plus delta x minus f of x divided by delta x when delta x approaches 0. This will be the solution of the first classical problem, finding the tangent line of a point on a function. We can see another example here is y equals f of x equals ax squared plus bx plus c. To calculate the limit of fx, simply take the limit of f of x plus delta x minus f of x divided by delta x. The result will be 2ax plus b, since delta x gets really close to 0 and can be omitted at this point. In other words, the derivative y is 2ax plus b. This is a very important technique to remember. Now, to solve the second classical function, which is finding the area under a line. So, if you have a curve and you draw multiple rectangles underneath this curve and try to fill up the area using these rectangles from point A to point B, you know how to find the area of a rectangle, which is width times height. Using summation to add up all the rectangles, you will find the area of the region, but there are so many empty spaces that we miss. But if we make the width of the rectangle smaller, you will be able to fit more rectangles in. And now you can see that the spaces left over have become smaller. Eventually, this means that when the number of rectangles approaches infinity, the area from all rectangles will approach the real area under the curve. Now that we have learned the importance of a limit, let's introduce the definition of a limit. Suppose that f is a real valued function and is a real number. This expression means that f of x can be made as close to L as possible by making x as close to A as possible. The equation can be read as the limit of f of x as x approaches A is L. But to prove that the limit actually exists, we must check for both sides. So when x approaches a from the left and also from the right, if they are both getting really close to L, this tells us that the limit exists when x approaches a. Suppose you have a function x squared minus 1 over x minus 1. When x equals 1, this function will be undefined. But let's say if you let x get very close to 1 from the left, for example, x equals 0.9999999, the function will be 1.9999999, which is very, very close to 2. And then you approach x from the right, so x equals 1.000000001. The function will be 2.0000001, which is also very close to 2. Because we cannot say when the function is equal to 2 when x is 1, the mathematical way to represent this would be to say that the limit of this function when x approaches 1 is 2. Based on the definition, we know that the limit only exists when x approaches a number from the left and from the right, and they both have the same results. Consider this function, y equals the absolute value of 1 minus x over 1 minus x. If we take a point at x equals 1 and approach this point from the left and from the right, the answers are not the same. In this case, we can say that limit does not exist at this point for this function, since the left and right are not the same. The formalized definition of the limit is known as the epsilon delta definition of the limit. Epsilon represents any small positive number so that f of x becomes arbitrarily close to L. F of x eventually lies on the interval L minus epsilon, L plus epsilon. The phrase, as x approaches a, indicates that we refer to values of x whose distance from a is less than some positive number delta, that is, values of x within either a minus delta a or a plus delta, which can be expressed with 0 is less than the absolute value of x minus a is less than delta. For any epsilon greater than 0, there is a delta greater than 0. If 0 is less than the absolute value of x minus a is less than delta, then the absolute value of the function of x minus L is less than epsilon holds. These are some basic rules of the limit. A limit of a constant will equal the constant itself. The limit of x when x approaches a is equal to x. The limit of x when x approaches positive infinity is equal to infinity. Vice versa for x approaching negative infinity. The rest are intuitive, but we shall keep all of these rules in mind as they will help in calculating limits in more complicated functions. Now, we will introduce the concept of differentiability in calculus. Differentiable means that a derivative exists and it must exist for every value in the function's domain. From this example, you can see that the limit does not exist, and this function is not differentiable at x equals 0. we know that the function domain can be from negative infinity to positive infinity, but not at 0, because it is not differentiable. These are some other examples of non-differentiable functions. For 1 over x, at x equals 0, it is undefined, so this is not differentiable. Another case is for x to the power of 1/3. When we take the derivative of this function and graph it, you will notice that at x equals 0, the derivative is undefined. Hence, this is also not differentiable. A limit might exist, but not necessarily be continuous at that point. Consider the example earlier from slide 6. The limit does exist because left and right both are the same results, but it falls on an unidentified point. Let's see one more example here to illustrate the definition of continuous. Where y equals 1 over x minus 1, when x equals 1, this will be undefined. As such, you can say it's discontinuous at x equals 1, so no limit exists at this point. When x equals another value, for example, when x equals 0, both left approaching and right approaching limits are equal to the same result. So, you can say that it is continuous at x equals 0. A function is continuous when, for every value a in its domain, a function might or might not be continuous depending on its domain. And it is always discontinuous at the roots of their denominators. All polynomials are also continuous. Here are some other theorems and rules that we should know. First, when fx and gx are continuous at point A, and c is a constant, 4 of the following functions are also continuous at A. The addition, subtraction of f and g, the multiplication of the constant c and f, the multiplication of f and g, and also for f divided by g when g is not 0. Second, all polynomials are continuous. All the rational functions are discontinuous at the roots of their denominators, as this means undefined. If g of x is continuous at a and f of x is continuous at g of a, then f of g of x is continuous at a. For the fifth theorem, when we factor out x at the numerator and the denominator, you will find that when m is larger than n, the limit goes to 0. When m is smaller than n, the limit goes to infinity. And when m equals n, the limit will be the constant. The definitions of asymptotes are also important to know, as they can help us in understanding the limit and graph of a function. When y is equal to L and the value of x is going to infinity, it has a horizontal asymptote. It can be the same for x goes to negative infinity. As for vertical asymptotes, when at line x equals a, and at that point y goes to positive infinity or negative infinity, line x equals a is the vertical asymptote of the function. This graph also has a horizontal asymptote at y equals L equals 0. In certain cases, the limit of a function may not be evaluated through simple substitution and doesn't offer an immediately obvious approach. One such case is that of the rate of sine x over x. Without proper understanding of these cases and their properties, evaluation may be difficult, if not impossible. In order for us to examine this specific example further, Let's first try to visualize a unit circle. This circle should include a tangent line extending from the origin past the edge of the circle to a horizontal value equal to that of the radius. Now, imagine a line drawn vertically from the top right corner down to the x-axis, and another to the left of that extending from the same height down through the point where the tangent line meets the edge of the circle. You should see something similar to this. If we look at the circle, we can see the overlaid segments described previously, each labeled for ease of reference. Pay attention to the segment PH. Though similar to its neighbor PA, it is just a bit shorter. Even longer than PA is the segment TA. But what do these segments have to do with sin x or limits? Notice that PH is actually sin x, PA is x, and TA is the tangent of x. So, we start with sin x is less than or equal to x is less than or equal to tangent x. Then, we can divide everything by sin x to get 1 is less than or equal to x over sin x is less than or equal to 1 over cosine x, which is the same as 1 is greater than or equal to sin x over x is greater than or equal to cosine of x. Finally, we take the limit as x goes to 0 and find that sin x over x is actually in between 1 and 1, or 1. So, the limit of sin x over x as x tends to 0 equals 1. Let's look at another example of a less obvious limit. 1 minus cosine of x over x. We can try working this one out algebraically, starting with the given function. Not a lot to work with here, as the limit just gives us division by 0. So, we'll multiply by the conjugate of the numerator. Multiply through on the numerator. 1 minus cosine squared x is the same as sine squared x. So, let's make that substitution. The limit of a product is equal to the product of the limits. And that leaves us with a limit of 0. D equals d over dx is a differential operator which operates in functions and follows the rules of differentiation. It is a linear operator, therefore, for given two functions, fx and gx, with two arbitrary constants, a and b, we have, first, we have the product rule. D over dx of fx times gx equals d over dx of f of x times gx plus d over dx g of x times f of x. To prove this, we use the definition of the derivative on the product. First, we need to manipulate things a little to get the proof going by adding and subtracting f of x times g of x plus delta x to the numerator. Then, we can break it into two pieces, factoring g of x plus delta x for the first piece and f of x for the second. Lastly, we take the limit of delta x as it tends to 0 to get the derivative of y equals g of x times the derivative of f of x plus f of x times the derivative of g of x. An example of the product rule. To take a derivative of y equals e to the 3x power times x to the third power plus 2x, we have f of x is e to the 3x, and g of x is x to the third plus 2x. Then plug in the formula of the product rule, and we have dy over dx equals d over dx of y equals 3e to the 3x power times x to the third plus 2x plus 3x squared plus 2 times e to the 3x power. The second rule is the quotient rule. We have d over dx of f of x over g of x equals f prime x times g of x minus g prime x times f of x all over g of x squared. To prove the rule, we can rewrite the quotient as a product, multiplying both sides by g of x to get f of x equals y times g of x. Then, take a derivative of f of x by using the product rule. Finally, we just need to separate y prime x into one side and the rest into the other and get the derivative of the quotient f of x over g of x. Example of the quotient rule. We have y equals sine of x over cosine of x, and we know that the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine x. So we plug it into the formula to get dy over dx equals cosine of x squared plus sine x squared, all over cosine x squared. We know that cosine x squared plus sine x squared equals 1 by its identity. So then, we have 1 over cosine x squared equals secant x squared. The third one is the power rule. To prove this, we also use the definition of the derivative on the power. X plus delta x power to n, we break apart like this. An x to the n power is cancelled out. Then, factoring delta x, we get this. Take the limit of delta as it tends to 0, so that all the delta x's cancel out. Then we get the derivative of x to the n power equals nx to the n minus 1 power. An example of the power rule. Example A, derivative of x to the 101 power equals 101x to the 100th power, based on the formula. Example B, the derivative of 8 times sine x squared is 16 sine x times cosine x. The last rule is the chain rule. D over dx of f of g of x equals f prime of g of x times g prime of x. To prove this rule, we'll use the definition of the derivative on the chain. And then, example of the chain rule. The first example is taking the derivative of the sine of 2x. Gx is 2x, so the derivative of 2x is 2. And the derivative of sine of x is cosine of x. So, the derivative of sine of 2 of x is 2 cosine of 2 of x. Second example, y equals tangent of x times secant of x to the second power. To make it easier, we'll take a derivative of secant of x to the second power separately. So we have the derivative of x squared equals 2x, and the derivative of secant x equals tangent x secant x. We'll get the derivative of secant of x squared equal to 2x tangent of x squared times secant of x squared. Now, just based on the formula, we have dy over dx equals secant to the 2x power. A function is the aggregate of a derivative. By looking into the derivative, we can learn a lot about the function's trend in a certain domain. When the derivative is positive, the function goes up. When the derivative is negative, the function goes down. Concavity can be used to shape the function. We can use concavity to predict a location of an inflection point. Local maximum or minimum must be at x0, where the derivative of f of x0 equals 0. The inflection point must be at x0, where the second derivative of f of x0 equals 0. However, the first derivative of f of x0 equals 0 doesn't necessarily mean that at x equals x0, the function has a local maximum or minimum. Example, y equals x to the third power. The second derivative of x0 equals 0 doesn't necessarily mean that at x equals x0, the function has an inflection point. Example, y equals x